Welcome to the DiRe research universe, where it's all about diversity and representation. The need to reduce inequality is ubiquitous. At least three of the United Nations Sustainable Development Goals are pertaining to reducing inequality. As the world moves towards achieving these goals, it is becoming increasingly clear that computers have a central role to play in this agenda. However, very little work is known to draw parallels between theoretical computer science and efficiently reducing inequality. Enter DRU. The aim of DRU is to clarify this all important path for us. If we take a bird's eye view of the journey into the DIRE research universe, we'll see that we have the ideation phase, the realization phase, a result phase which we hope to reach after a relatively longer journey, and the origin phase that will discuss the why and how DRU came into existence. The aims during the ideation phase were relatively simple. First was to understand the difference between diversity and representation, and second was to understand the computational complexity of the model by getting hardness results from a single NP-complete problem, namely the vertex cover problem on three regular graphs. So the two aims were understanding the difference between diversity and representation, and using the vertex cover problem. Having diversity and representation and the vertex cover problem. We had diversity and representation, and we had the vertex cover problem. I'm sure you get where I'm going with these. These were not two separate discussions, and we eventually realized, after spending a lot of time with the beautiful vertex cover problem, that vertex cover problem and reducing inequality using diversity and representation are indeed equivalent. But how is that so? On the surface, the vertex cover problem on D-regular hypergraphs and K-uniform hypergraphs may seem equivalent. However, on zooming in, theoretical computer scientists have shown that the vertex cover problem on D-regular hypergraphs is very different from the vertex cover problem on K-uniform hypergraphs. Similarly, reducing inequality using diversity and using representation is as different as the vertex cover problem on D-regular hypergraphs and on K-uniform hypergraphs respectively. Now that we understand that vertex cover and reducing inequalities are indeed equivalent, but so what? This is where we are moving towards the third phase of DRU, which is a result. Having established this equivalence, we realize that if we get an unconditional deterministic polynomial-time algorithm for the vertex cover problem on unweighted simple graphs with vertex degree at most 3, we will indeed be able to efficiently reduce inequality. Let us do a high level hand waving to what this sentence in front of us means. Let us start with an unconditional deterministic polynomial-time algorithm. As an example, consider the graph shown on the screen. Vertices 1, 2, 3 and 6 form the minimum size vertex cover. Let us study this graph. We start with maximal matching, which is equivalent to the 2 approximation algorithm, which is very famous among computer scientists. Here in this algorithm, the task is simple. We arbitrarily pick an edge from the graph and store the 2 vertices in a set that are connected by the picked edge. I kind of tweak the maximal matching algorithm a bit by also storing the edges that are connected to the vertices picked that were endpoints of the edge picked during maximal matching. Simply saying that we pick the edge connecting 0 and 1, then simultaneously I will also store the information of the edges that are connected to vertex 1. Next, let's assume we arbitrarily pick edge connecting 4 and 6. Then we connect the edge connecting vertices 2 and 7, and eventually we pick an edge that connects vertices 3 and 5. So the set of vertices, these 8 vertices, form a vertex cover. It is known, it is a 2 approximation algorithm. So here the vertex cover of size 8 is twice the size of the minimum size vertex cover. However, I'm not happy over here. Like, there's a lot of information on the right hand side set of vertices that can be used to optimize the size of the vertex cover we get. So we zoom out in the algorithmic space to kind of have a local minimization phase, wherein what we do is for each row we remove the vertex that may not be needed. How do we select that? Consider the last pair of vertices, vertex 3 and vertex 5. We know that vertex 3 is connected to some other vertex in the graph, and vertex 5 is only connected to vertex 3. Hence, if we remove vertex 5, and in this phase, vertex 3 will still be covering the 2 edges that are in question. So we remove vertex 5 from the graph, from the set of vertices that we have. And 3 is still a vertex cover in this local graph that we have. Similarly, for the pair of vertices 2 and 7, if we remove any one of the vertex, let's say 7, then 2 still covers the edge in question. For the next pair of vertices, that is 4 and 6, we cannot remove any vertex, because then at least one of the edge will remain uncovered. And for the next pair of vertices, if we remove 0 and keep 1, then we still have a vertex that covers all the remaining edges. So here we can clearly see that all the edges are covered, and now the size of the vertex cover has gone down from size of 8 to size of 5, which is almost optimal but not yet. So we need to do something. We need to handle the arbitrariness in the edges picked during the maximal matching phase. So how can we remove that arbitrariness? We zoom out further in the algorithmic space and use breadth first search. We kind of inherently provide an order in which the edges are picked during each iteration of the maximal matching phase, which will be helpful during the local minimization phase. We start with vertex 0. We pick edge connecting vertices 0 and 1. Among the remaining vertices, vertex 2 and 3 are on the next level of breadth first search. So we zero in on, let's say, vertex 2, and then again arbitrarily pick an edge that connects vertex 2. So we can either pick the edge that connects vertices 2 and 7, or pick an edge that connects vertices 2 and 4. Let's say we pick the edge that connects vertices 2 and 4. Finally, we pick an edge that connects vertices 3 and 5. So again, we have 6 vertices that form a vertex cover for sure, but still this is not minimum yet. So what we do is something that we did previously. We remove any vertex at each level, removing which will not affect the set of vertices being a vertex cover. So here we remove vertex 0, and this set of 5 vertices is still a vertex cover. But again, we shouldn't be happy with this, because this is still not the minimum size vertex cover. So what can we do? Yes, we zoom out further. And finally, we bring in maximum matching. We find the edges that are part of the maximum matching using the beautiful Blossom algorithm. And now after BFS phase, which edge gets picked will also be determined in a very specific way instead of that arbitrariness that we had previously. So store this information of the edges that are part of maximum matching. We do BFS, we start with 0. We pick edge connecting 0 and 1. Next, on BFS we have vertices 2 and 3. For vertex 2, now we specifically pick an edge which is part of maximum matching. So we pick vertex, the edge connecting vertices 2 and 7. Next, we have 3 on the that is part of the BFS. So we pick the edge connecting 3 with 5 as it is part of maximum matching. And finally, we are left with an edge that connects vertices 4 and 6. Now, because we determined the order in which the edges are picked, and also within that ordering induced by BFS, we also introduced the notion of which edge gets picked. We move to the local minimization phase. Here in among vertices 4 and 6, let's say we keep vertex 6 and we make a slight modification to local minimization phase by including all the edges that were part of the vertex 6 at this level and removing it from any of the above levels that we had. Hence, the edge connecting vertex 5 and 6 is now connected to 6. So that frees up 5 for us to remove. Next, we remove vertex 7 and we remove vertex 0. Here we can see that all the 9 edges are being covered by 4 vertices, which is the size of the minimum vertex cover. Yes, we are happy. We have a minimum vertex cover. We have an algorithm that is able to find the minimum size vertex cover. But caution, the journey is not yet over. We have not reached the end of the phase 3 of the DiRe research universe. That needs some more work in the local minimization phase that we just discussed. I'll digress on the technicalities over here. Now let me quickly take you through how I zoomed in on the specific set of graphs that we are using. I started with this huge family of graphs where we have hypergraphs, we have directed graphs, we have weighted graphs, we have unweighted graphs, all those things. But I decided to focus on unweighted, undirected graphs, and I was a happy camper because a huge family of graphs were already removed from consideration. However, unconnected components and multiple edges and loops were creating a lot of headache while designing the algorithm. So I decided to focus on unweighted, simple connected graphs. But again, allowing or giving the leniency to vertices to have as many edges they wish was again becoming a huge headache. So I decided to further zoom in on unweighted simple connected graphs with vertex degree of at most 3. The vertex cover problem on these family of graphs is known to be NP complete, so we still are working on an algorithm for the vertex cover problem, a variant of which is known to be NP complete. Now the road ahead. The most obvious thing that comes to mind is to further zoom out in the algorithmic space. Means after all, we have 132 more graph algorithms that we can look at. But no, I won't be doing that whatsoever. The next step is very simple. We have to update the local minimization phase that I cautioned you about. For which I plan to use adjacency metrics to get details on the neighbors that are being used. Again, the details are not important in the context. I'll show that our work overcomes all these traditional barriers in complexity theory. It is not affected by the lower bounds that have been widely discussed, and all these both these things would have been important if my proof was on showing that P is not equal to NP, which is not the case. And in the worst case, if we hit a dead end, we can modify the algorithm to make it a randomized algorithm using Ramanujan graphs that correspond to 3 regular graphs, and Ramanujan graphs are known to be one of the best kinds of expander graphs. Some of the sanity checks of this work: we are working with the closest cousin of a problem in P, namely the vertex cover problem on 2 regular graphs. There are multiple approximation algorithms possible out of the algorithm which we are working on, which will improve the bound of the 2 approximation algorithm that we have. Even more beautiful thing is that our tool or our algorithm is a very simple amalgamation of tools previously developed. For example, the 2 approximation algorithm and the Blossom algorithm developed by Edmonds. There is nothing groundbreaking. We are just mixing all the different algorithms that are part of in this algorithmic space, the humongous algorithmic space that we have. And the algorithm already kind of handles all the edge cases and the spatial cases that we have. So finally, we have the origin. Why did this project come into existence in the first place? Here, the idea is to propose a theory of selflessness, which is a study of non-zero sum many player games where each player disregards their own utility. Now, this selfless modeling of agents is very different from the rational and the altruistic players that have been widely discussed in game theory, but I'll digress on that front for now. And this basically gives a very high level non-technical summary of the journey in the DiRe research universe, which I aim to continue. And eventually the idea is to reduce inequality and make this world a better place, hopefully using beautiful tools from theoretical computer science. Thank you.